Alrighty, I counted the number of requests to review one of the scores I made on the Fleamarket a few weeks ago, and let's say most of the requests were all about this one here. Yes, indeed, it's all about the RCA multimeter, and to be more precise, the senior Volt Ohmyst WV98-A, as you can tell over there. I'm not entirely confident that we will find a pristine mechanism on the inside. But that being said, this was a find on a flea market, so it wasn't a buy from a reputed seller or something like that. So what I suggest is that we dive right in and have a look what we find inside. Okay, for safety's sake, I removed the buttons from the front. Well, because you never know, once we open up the case and we try to pull out the mechanism, that the knobs might obstruct that. Now, the weird thing is, this plastic looks moldy almost. It has this fine white crud on top of it. Now, come to think of it, I did see something very similar on another channel. Maybe some of you know it. It's Bob Anderson's channel, where he repairs all sorts of black and white TVs and radios. And I seem to remember he made the same remark about some knobs he pulled off some appliance, and it looked just the same like this. Apparently some sorts of plastic seem to, well, develop this kind of whitish mold, let's say plastic mold, and it really depends on the type of plastic they used. Anyway, it just comes right off the shaft of the knob, so there you go. So those shafts on the front, and you can see a little slot on top there where this little spring thingy would fit in. Now it turns out one of these knobs is missing this little spring, so that's sort of annoying. Anyway, enough jabbering. Let's get into the machine itself. I did not open it up before, so what you're going to see is what I'm going to see for the very first time. So, okay, that's one screw. Now, I did say a few minutes ago that I suspect somebody has done, well, a few modifications inside this apparatus, and I'm just, you know, crossing my fingers that whomever did it with full knowledge of the matter and did not screw it up. Let's see what's hiding underneath, eh? Okay, there you go. Whew. Now that is one massive case. I mean, look at it. It looks like cast aluminum, and I would say it's a goodly 2 or 3 mil thick aluminum. Wow, they didn't do things by half, that's a fact. Nice. And okay, so here is the mechanism. Let me show you. Alright. Well now. So this is how it looks on the inside. Okay. It seems to have... Okay, so this meter has two tubes, okay? It has an, if I'm not mistaken, a 6AL7 and a 12AU7. And indeed, those are two mini tubes, okay? And you see them there. Now, right now, at this moment, I can't tell you whether the tubes are still good or not, but I can't see gather, but they don't look gassy to me. So my first my instinct would be to say, okay, probably the tubes are still okay. So anyway, I told you that this cable didn't look original, but it might be, okay? So by the way, the 12AU7 is a double triode, and the 6AL7 is a double diode, so rectifier tube. And if I'm not mistaken, the rectifier tube is this little tube right here, and the 12AU7 is this one here. We'll see in a minute. Okay, so at first glance everything seems to be okay. There's one thing that I noticed, that somebody here wrote plus 1.5 volt, which makes me suspect that they modified this multimeter not to use a battery. I mixed a batch of soapy water, which is really nothing but a bit of detergent, just simple dishwashing detergent, and some water, some tap water. And I happened to have a bottle which was nearly empty of detergent, and I just filled it up with water, and there you have it. The perfect mix. So let's throw in the knobs of the RCA, fill the ultrasonic cleaner up with some water. There, that should be enough. And I'm going to program the ultrasonic cleaner for, I'd say 30 minutes. Let's see. 18, 21, 24, 27, 30 minutes. So there you go. Let's see how the knobs will end up. Okay, this multimeter presents us with a few mysteries. Now, I'll let you watch the schematic of the multimeter, and I'll have you guess where the reference battery, because it needs a reference battery, is connected to the circuit. Yeah, it needs a 1.5 volt reference battery. Well, if you haven't found it by now, let me tell you, you won't find it in at least 10 or 15 minutes. I had to look for it myself for a long time, until right down there I found the symbol for the battery. Let me show you from closer up. there. You see? Yeah, that's the symbol for the reference battery. Now you'll notice that on the schematic there's neither a negative or positive marked. I did some research on the internet, and it would seem that the battery is indeed connected with its negative side to ground, or to the chassis in this case, and with its positive side to this row of resistors. So you'll notice that, and that's the next mystery, you'll notice that all these resistors going from 9.75 ohms all the way up to 10 meg are connected to a row of contacts of a multi-switch. Notice this code number here, S2C. Now have a peek at the multimeter itself. This plate here is marked as S2D. If you can focus. Okay, so this back plate here is marked as S2D. So it stands to reason that the plate behind it should be S2C. Let's have a look if we can see any kind of code. I think, oh yeah, there it is, but it's hard to see. It's down there between the two plates. It's, well, I don't think I can show you like this, but trust me, the code S2C is down there on this plate here. Okay, in any case, if you look at the schematic, you'll notice that the positive of the battery is connected to this whole row here of resistors. Now, that would mean that if we look at the multimeter, can you see this? Yeah, I think you can. Yeah, I think you can see this. Okay, so this wire here is supposed to be the positive of the reference battery, the same one we saw on the schematic over there. And oh, by the way, this little black wire here, this little stub here, is all that's left of the negative of the reference battery connector. That you'll notice that the battery holder itself is gone. So we'll have to make something for that sooner or later. So if you look at the schematic, you'll notice that the white wire, so the positive lead in fact for the battery, is connected to the common of all these resistors. So the common of all those resistors is this row of contacts right here. Yeah? I think you can just about see it. Let me see if I can zoom in. Okay. There you go. So you see the rows of contacts on top there are all connected through. Right, so and this positive wire here is connected to it. Let's check it. Let me zoom out again. Can you see this? Let me see. Yeah, you can see this. Okay. By the way, by the same token, we're going to test out a new multimeter I bought. The brand is an Helix. It's a model 15152. it's not so different from my Vicky, my trusted Vicky, which I've had now for, I'd say 4 years or so. So usually I use my auto range Vicky, and I'm very happy with her. But for one detail, Vicky has the tendency to switch off and beeping whenever it's going to switch off, and my Helix, the new one, will not beep before it switches off. In fact, it won't switch off because as you can see here, it's marked APO, automatic power off, but you can switch off the auto power off, and that's exactly what I did. So if it's on auto power off, you see in the top left of the screen APO. But I hate that annoying beeping, so there you go, I can switch it off. Nice, eh? Okay, so back to our multimeter here. So let's see if this white wire, which is connected to the positive of the reference battery, connects indeed to the common of all those resistors on the S2C plate. Yep, it does. Okay, I connected the Helix like a continuity tester. Okay, let's see if I can show you both in the same shot. Okay, here we go. So okay, so yeah, let's see. Right, so it is connected to this row up here. This row up here, in fact. Okay, so now, yeah. So now we're going to go from the common to the resistor you see here. And I'm not going to try to turn it, but I think it's a 10 mega ohm. Let's see. Okay. So, and no, it isn't. Do you see what I notice? So I'm measuring, in fact, from one side of the resistor to the other, and I get a short. Actually, I don't get a real short. It's something like 10 ohms or so. Yeah, there you go. 10 ohms. I don't know if you can see it. It's a bit dark, but which by no means is a guarantee that the tubes will work. But I wanted to check whether their filaments are good or not. So I'll show you. Okay, I think you can just about see the meter here. So for the 6AL5, this one, you measure between pins 3 and 4. Yeah, it has the filaments connected to pins 3 and 4. So 1, 2, 3. And pin 4. And we measure 3.3 ohms. Okay, so this is good. Oh, and by the way, it still has its getter. If you look carefully here, you can still see the getter here. So this tube is not gassy. Okay, so now the 12AU7, so this was the 6AL5. This is the 12AU7, and it's still the original, I think. So it's an RCA, right? So, and it reads here 12AU7A. I don't know what the end A means. Maybe sort of a type of sensitivity. In any case, the 12AU7's filament pins are the pins 4 and 5. So 1, 2, 3, 4. Remember, always count starting from the key. Okay, so the key on a tube, let's see if I can show you. Can you see this? Yeah, you can see this. So the key on a tube is always the large opening between the pins, okay? So if you start to count, you always count clockwise if you look at the bottom of the tube. So 1, 2, 3, 4. Alright. And then pin 5. Alright, and that gives us 11.912 ohms. Now if we measure between, say, pin 4 and pin 9, we should get about half. See? Yeah, 6 ohms, and now we measure between pin 5 and pin 9. Remember, pin 9 is a common. So now we measure pin 9. Come on. There you go. That's 6.5 ohms. Okay. So I would say the filament on this tube is okay. Well, actually, the filaments, both filaments, okay, and the getter is fine as well. You can see it right here. Right, so, oh, and the small tube, I don't know if it's an RCA, let me see. Oh yeah, how about that? It's also an RCA tube. So probably both these tubes are the original ones. This is the power supply of or let's say part of the power supply of the voltmeter. And if you look carefully, you'll see it only has one winding here, yeah, and it clearly states down here 117 volts. Now this transformer here, its primary winding should only have 2 wires, right? Right. Now have a look at this one. This one has 4 wires. So if you look here at this bunch of wires here, it has a black one here, then a white and black one, a red and black one, and a yellow and black one. Alright, the black one I determined is probably the common, or so you think. Now if you go up on top, you see the black wire, you see the white and black, the red and black, and the yellow and black. Okay? Okay, now have a look at this. Now watch what the meter says when I touch these wires here, the white and black and the red and black, which are tied together. Look at the meter. Come on. Make contact. Yeah. There you go. 0.12 333 kilo ohms, so 333 ohms. Now watch what I measure when I measure with the other pin. Here it says 0.366 ohms. So one side measures 333 ohms, the other side measures 366 ohms. If I measure between those two pins here, this pin and that pin, I measure 690, well, almost 700. Okay, so if I measure between these two, I measure 600. If I measure between these two, 333, 366. Okay, so why does the transformer have 4 wires? Why? My guess is it's likely that it is a 220 transformer after all, and not a 110. And remember, we had a look at the rivets which hold the transformer to the chassis. So yeah, in all likelihood, this is probably a 220, but I'm still not 100% convinced. Okay, the final mystery for now is this. Right here, you see this here. This is a diode, all right? So let me close up. So this here is a diode, all right? All right. Now, I'll confess that for a while at least, I looked all over the chassis for a diode. And frankly, at first glance, I couldn't find any bloody diode. No matter how much I looked and looked and looked, I couldn't find a diode until I started to follow the wire. Yeah, or well, one of the wires of the secondary. And one of the wires of the secondary is this one here, which leads straight to that diode. Alright? Wow. Where is that wire? Well, that wire turns out to be the one, let me see. Can you guys see that? I think you can just about. The wire we are looking for is this wire here. This one. It's a yellowish red one. Okay? Now watch where that wire runs to on top. Can you see it coming through that opening down there? That round opening down there? Well, not too good, but can you see which pin it connects to? That wire, that yellow-red wire, connects through to that pin here. And I'm certain right now there are quite a few people saying, oh yes, now I see what that is. And indeed, after a minute or so, my penny dropped as well. This, my friends, is an old style diode, this here. Yeah, a selenium diode. In fact, you know, it's those old style diodes are a stack of metal plates with in between some semiconductor material. Yeah, some oxide. Yes, indeed, the diode on the schematic is this. It's a selenium diode, and these are notorious for being very, very bad. Without disassembling the whole multimeter, I really needed to make sure that the transformer you see down there is indeed intended for 220, okay, and not 110 like the American counterparts of this multimeter. So what I did was I connected it up to the power block over there, the orange one you see in the corner, which is connected to my variac, and for the moment it's not outputting too much power, 44 volts and no current. Okay, anyway, I reasoned that if this transformer is in fact an American type power transformer, that at 110 volts on the primary coil I should get around about 6.5 volts on the filament secondary coil of the transformer, and that's what I'm going to measure. So I set up my multimeter to measure the filament voltage right on top here. Okay, so I set it on the socket of the 6AL5 tube at one of the filament connectors, and I'm going to switch it on and slowly feed up voltage through my variac you see over there, and at the same time measure the filament voltage. So let's just do that. Yeah, let's switch it on. Okay, and right away I'm measuring 1.4 volts, and the variac is pumping in 43 volts. So let's go up to 80. And there's no current being drawn, but that's normal since there are no tubes in the multimeter. Okay, we're at 80 volts AC on the primary coil, and I'm measuring on the filament coil, so the secondary, 2.57 volts. Could it be a European transformer after all? Let's go to 110. Come on. Yeah, my camera is having a bit of trouble with the lighting here. Okay. Okay. 116. That should be the regular American voltage. Ha! 3.68 volts filament voltage. That's not enough. That is certainly not the voltage you would expect. I would expect something around 7 volts or so. Filament voltage, and well, that seems to suggest to me that it is indeed a 220 volts transformer. So let's go. I feel quite confident that I can go now all the way to, say, roughly 220, there, 224. Ha! There you go, 7 volts filament voltage. Yeah, that's yes, that's the right filament voltage. So indeed, it would seem the transformer is in fact European. That's nice. At least that way I know that well, that the transformer isn't ruined and that it makes sense to try to clean and restore this multimeter. Okay, the variac is at 110, so let's switch on everything here. Okay, right, so we're at 110 volts. So I connected up my multimeter on one hand to one side of the rectifier, this one right here. Alright, so in fact what I'm measuring here is this end. Really, let's see, this end here, and I connected up my other wire to the other end of the secondary coil for the high voltage, so this end right there. Alright, so let's switch it on. 64 volts, right, but we're at 111 volts AC in, so let's go to 220. Yeah, well, yeah, there, 224. Alright, so the AC voltage, the high voltage, is 127 volts that I'm measuring right there. Yeah, and we're inputting 223 volts AC. Now, I'm really curious to see whether the rectifier still works. You know, that little selenium rectifier you see over there. Because those are notorious for breaking down. Well, that's quickly done. Let's switch it off. Alright, no more voltage. Now let's set the multimeter to DC volts. 1000 volts DC. Okay. These reflections, they really kill me. Okay, and now let's measure on the other side of the rectifier. Let's see what we measure now. I'm curious, and I think you are too. Okay, 139 volts DC. So it would seem the rectifier works still. Weird, because I tried to measure it out and it would not register at all on the multimeter. So apparently selenium rectifiers are a bit hard to measure passively. Fine, okay, so it means the rectifier works, but I'm not going to keep on using it, because like I said, those little rectifiers are really notorious for breaking down, and when they do, they smell horribly, I've been told. And well, generally speaking, you know, this is high voltage, and I would prefer a slightly more, how to say, a part which is more reliable than something like this. So I am going to replace it by a silicon rectifier.